In probably this final video, we're going to look at a scenario of an object on the outside of a circle and its motion. So just to give an example, a car going over a humpback bridge, it leaves the ground if it's going too fast. You know, you've all driven over humpback bridges, and you get that sort of negative G type feeling in the belly. Imagine, you know, how fast was that car going in order to do some air. And we're going to look at questions like that. We're also going to look at questions where we have an object on the outside of a cylinder, and if we were to let it fall off that cylinder, what is its motion? So in this instance, we're talking about the bridge is the shape of a circular arc, okay, and the idea is what speed must it be doing in order to stay on the actual road, as opposed to sort of lifting off and jumping. Okay, doing some air. Okay, so a bridge is in the shape of a circular arc, radius 20 meters, as shown in the diagram. What is the greatest speed with which a car can travel over the highest point of the bridge without leaving the road? Okay, so we're going to need to draw some diagram and get some sense of what's going on. So if you think of the object, it has a mass, and gravity will mean it will have a weight that will be vertically down, and there's going to be a separate reaction, I'll do this in red, from the surface up. Okay, so the reaction of the surface on the object, and then likewise we've got the gravity causing a force acting down. So the idea here is, as before, circular motion is going to cease when one of the forces is equal to 0, and in this instance, again, the idea is we're looking at the idea of the reaction of the road on the object being equal to 0, and at that moment in time, you've got your sort of maximized situation. Okay, so circular motion is going to cease when some force reaches 0. We want to imagine that there is some centripetal force, and so towards the center of the circle, what are the forces acting? Well, gravity is acting towards the center, the reaction is acting against that, so it's minus R, and that's going to equal the mass multiplied by V squared divided by R. We know what R is 20. So we can substitute that in. We're for the purpose of this sort of this limit situation, we're saying that R is equal to 0 to cause that moment where it's about to lift off. We can divide by m both sides and multiply by 20 to get rid of the denominator, and we get v squared is equal to 20g. If we then square root that, we will get an answer. Okay, hang on, and that works out as a nice tidy 14 meters per second. So if it's going faster than 14 meters per second, then it's going to lift off. Basically, it's going to leave the road. If it's going at a speed less than 14 meters or equal to 40 meters per second, it's going to stay on the road and it's going to just carry on over the bridge. Now, just before we move on to the next question, let's just sort of talk about a scenario. Let us imagine we have an object sitting on top of a cylinder and just happily sitting there, and then we give it a nudge, very gentle nudge, so we're not trying to give it any velocity, we're just, I suppose, getting it just over the apex, just so that gravity is actually going to start pulling it down the side of the circle. Imagine this is a cylinder. Okay, so what's going to happen to its movement? It's going to come down the side of the cylinder, and then what's it going to do? So at some point in time, it's going to leave the surface, because what it's not going to do, it's not going to carry on underneath. See if we can actually move. It's not going to go in underneath the circle, okay, underneath the cylinder. It's not going to end up there, right? Okay, at some point in time, it's going to leave the surface. So where is it going to leave the surface? Well, I suppose it depends upon what speed it's going at when it's nudged. If it's got an impulse of actually a movement, okay, of just enough, it's going to go slowly. It's going to speed up, speed up, speed up. So what's going to happen now? If it's going a bit faster, what's it going to do? Is it going to leave earlier? We talked about a car sort of coming up over and then just literally we saw the rally car just lifting off literally. So there's going to become a speed at which it's going to leave the circle, even if it's going really slowly and just speeds up. Okay, will it get to this point here and then just drop straight down, or it won't leave it afterwards? So it's the last possible point that it could leave contact with the cylinder. Will it possibly leave earlier? Will it sort of end up sort of flying out at the end of the day? If it's getting a velocity going, it's got both a horizontal velocity and a vertical velocity. So are we saying it's going to have no sort of horizontal velocity? Even though it has it up to now, all of a sudden it's going to the right, but all of a sudden it stops going to the right and it goes straight down. Is it going to go straight down, or is it going to at some point in time going to leave and actually land further away from the circle, from the cylinder? So that's what we want to look at. So we're going to look at the point right at the top, at the apex, and we're going to talk about a point somewhere, okay, at the side where it's going to leave the surface. Okay, so is it 90 degrees from the vertical, or is it something less than 90 degrees? That's the question to ask. So wherever it's losing contact, we're going to be talking about the fact that at that moment in time, the reaction of the cylinder onto the object is going to equal 0. mg is acting, and depending upon what the angle theta is, you have your two components. Let's use a different color. I don't know which color I'm going to use. So you've got your component of your gravity towards the center. That's going to be mg cos theta, and then in the other direction you've got mg sine theta, because that angle in there is going to be theta as well. Okay, you've got your z, your alternate angles. So the force of the gravity towards the center of the circle is mg cos theta. The force perpendicular to that is mg sine theta. We're not really interested in that bit. It's only the mg cos theta we were interested in. The other thing to be just conscious of is the movement. So we can think about that movement, the vertical height that it has changed by. So if we think about our triangle, we've got our radius, okay, and we've got another radius here. So how can we describe this distance here? So if we appreciate that this is theta here, then we can take this adjacent side. It's going to be r cos theta. This total distance is r from top to bottom. So the difference, the height that it has changed by, okay, so the change in height in this instance is going to be equal to, so delta h is going to be r minus r cos theta. R minus r cos theta. It's going to be that change from the top moment to the top point, to the point where it leaves the surface. So we're going to use that idea in the next question we're going to work through. So a particle of mass m is at rest at the top of a smooth sphere, center 0 and the radius of 3. The sphere is fixed on a horizontal surface at B, where AB is the diameter, and the particle is displaced slightly from rest and travels down the sphere, losing contact with the sphere at point C and landing on the horizontal surface at point D. So the question is what's the angle? So basically AOC, you can just about see it there. What's this angle here? That's what we're interested in. We're interested in that angle. They've called it alpha. So show that cos alpha is equal to 2/3, where alpha is the angle between the radii OA and OC. What can we do? So there's been two things, generally speaking, we've been doing. We've been looking at the energy differences, or the transfer energy from potential to kinetic, and that sum total of energy, and we've also been looking at the forces acting. So we'll start off with the energy. Generally speaking, that's usually your first port of call. So again, we've got potential energy and kinetic energy at the start at our point A. So if we take it that its velocity at the beginning is equal to 0, we can say that its height above the ground is 6, because it's 2 lots of the radius 3. So we can say the height is 6, so 6 mg. The velocity is 0 at the beginning, and the potential energy and the kinetic energy at the end. Well, we don't know what its velocity is at the point that it leaves the surface, and the height that it is at now is going to be, well, as I talked to you previously, you can think about it. You've got that triangle where you've got 3 as your radius. So this is going to be 3 cos alpha, that distance up the side. If we add on the 3 that's below, we end up with a height from the bottom of 3 plus 3 cos alpha. So here, I know previously when I was just discussing, I was talking about the distance it's moved, but what we're really interested in is the distance it is from the ground. So it's the 3 cos alpha plus the 3 that takes you from O to B. So total height from the bottom is 3 plus 3 cos alpha. If I double everything and divide by m, I get 12g is equal to v squared plus, and if I open up the brackets as well, so it's going to be 6 lots of mg and 6 cos alpha lots of mg. I'm dividing by m, so it's 6 lots of g and 6 cos alpha lots of g. So as a result, I don't really get everything I need, but what I do get is an expression for velocity, or velocity squared, should I say. Combining like values, I get 6g minus 6g cos alpha. So that's looking at energy. Now we're going to look at the forces acting, and again, at this stage, you should realize this centripetal force equals mv squared over r. We can use this expression for v squared. That's our link and connection between our energy formula equation and our forces equation. So it's probably wise for us to draw a little diagram of the forces that are acting. And so on our circular surface, our object has a gravity component towards the center of mg cos alpha, and we have the reaction going in the other direction. Now our reaction is going to equal to 0, but if we just write out our formula, we've got mg cos alpha minus r is equal to mv squared over r, so the radius, okay, not the reaction. So I'll put that 3 straight in there. And now if R is equal to 0, we end up with mg cos alpha is equal to mv squared over 3. Now arguably I could now substitute actually in my v into that from the previous part. So I can put in the fact that it's 6g brackets 1 minus cos alpha into there. I can divide both sides by m to cancel them out. You'll see that I can also cancel out g as well. So those g's cancel out. And I'm left with cos alpha is equal to 2 lots of 1 minus cos alpha. I suppose if I now expand that. Now, some people, you didn't need to have that bracket in the first factorized, but we end up cos alpha is equal to 2 minus 2 cos alpha. That gives us 3 cos alpha equaling to 2. And therefore, we have, running out of space, we've got cos alpha is equal to 2/3, which is what I was asked to prove in the question. Yeah, it stated, show that cos alpha is equal to 2/3, where alpha is the angle between the radii OA and OC. So that's the hard work done. So just in summary, I went through the energy equation, the conservation of energy, potential energy and kinetic energy before in sum total is equal to the sum total of the kinetic energy and potential energy at another point in time. And then we said at that point where it leaves the surface, R is equal to 0. One of the forces is equal to 0. It's not going to be gravity because gravity is always there. So we then worked our through using R equals 0 in our basic formula for the centripetal forces. We're able to get the angle at which it leaves. And just for the record, if I worked out what alpha is, the inverse cos of 2/3 is 48.2 degrees. So not far off an eighth of a turn around. So halfway around that sort of quarter turn, it actually leaves the surface. Now you'd think it would actually leave the surface later, maybe even at 90 degrees, but it doesn't. It leaves quite early. It leaves at 48.2 degrees before it starts becoming a projectile. Okay, so the question moves on to asking what is the speed of a particle when it leaves the sphere. Okay, so, well, we've got an expression for the angle. We've also got an expression for the velocity. So just to remind us that there you go, we've got v squared is equal to 6g 1 minus cos alpha. Well, we now know what cos alpha is. Cos alpha is 2/3. So that velocity at that moment in time is 6g 1 minus 2/3. So it's 1/3 of 6g, which works out as being 2g, and therefore v is equal to the square root of that. Now, whatever that works out, that's 2 times 9.8, or square rooted, gives us 4.4, correct to 1 decimal place. I'll do 2 decimal places, 4.43 meters per second. But I mean, the square root of 2g is fine. Then lastly, the last part of the question was find the speed of the particle as it hits the horizontal surface at point D. So let's remind ourselves, it flies out and it's going to be a projectile and it's going to land. What's that velocity when it hits? Well, we're down on the ground, so we have a situation in part 3 whereby our h is going to equal to 0. So energy beforehand, right at the beginning, it was 6 mg with no kinetic energy. And at the end, it has no potential energy, and all it has is kinetic energy. So this is a different V. So V1 is the point where it leaves. V2 is going to be when it lands. So if I double everything, and if I divide by m, and if I do the square root, So what is the square root of 12g? We end up with square root of 12g is equal to my v is equal to, now just very quickly I could tidy up that surd, so it's 2 root 3g, but that's equal to 10.84, correct 2 decimal places.